again, I'd love to come back and show you, this is an experiment, maybe next time I'm in town, but realizing the triple point of water is kind of fun, because you get a thermodynamic plateau where the temperature is exactly the same. You hit a plateau because all of the energy, if it heats up, the energy just goes into phase transition from solid to liquid, and if you cool it down a little bit, all of the energy goes into phase transition from liquid to solid, and it stays the exact same temperature down into the microkelvin as best as we can measure it. So we manufacture triple points of water cells for realizing the international temperature scale. We also manufacture fixed points at the freezing point of tin, zinc, and aluminum and silver, going up to the high end, and on the low end we make the triple point of mercury and the triple point of argon, which is about minus 187 degrees Celsius, that are used as the defining points for the measurement system. And then of course you need a thermometer to measure them. That's this device called the standard platinum resistive thermometer. Fluke builds those too, and we also build the nice little display unit to be able to measure temperature for that process. So we're very much involved in that. So we're interested in changes in Kelvin, because what does that do to us? But we also understand the Kelvin is kind of a pain. So how do we solve that? Well, off to Germany. So the Germans had proposed that, hey, let's use the Boltzmann constant for defining the Kelvin. It's really kind of a nice constant to be able to use. It pops up in the ideal gas law. It goes into quantum mechanics. It's used everywhere. It's kind of nice, but the problem is on that is we haven't measured the Boltzmann constant well enough to be able to want to make it exact enough to be able to cut the line in that. So the Germans wanted to go about doing this process. Actually, it's an international collaborative effort once again too. And what they did is they wanted to do one of their experiments was to make a determination of the dielectric gas constant of helium at 7 megapascals. Yes?
So is the pressure measurement really good as well, comparatively?
Exactly, because it's defined as 7 megapascals, and the accuracy of your pressure is got a sensitivity coefficient of 1 with the output of the experiment. So if it's off by a part per million, your experiment's off by a part per million. So that was a real challenge. And in fact, at that process, so they said we want to measure pressure accuracy at 7 megapascal, which is about 1,000 pounds per square inch, approximately. So they wanted to measure about 1,000 psi, and the problem was that there wasn't anything good enough to measure that. So, guess who they called? Yeah, off to our Phoenix, Arizona location, they called Fluke, that happens to make the world's best pressure standards. And the challenge was, though, at the time, that the world's best pressure, and this is called a pressure balance or a deadweight piston gauge, where we're realizing first principles of pressure, force over area, or force times mass times acceleration of gravity in that process. And so it's really in the geometry of the piston cylinder that creates that area computation. That's the real trick. The challenge was the world's best measurements at the time were about 4 or 5 parts per million at 1 sigma. For that process, and they wanted less than 1 part per million, 1 sigma for that process. So we said, yeah, improve 500% off the world's best measurements, sure, but actually our engineers and scientists did it, and we were able to produce a pressure balance that met that requirement for them, so they were successful in that experiment. And that number is carried forward as part of the redefinition as well. And we're pretty excited to be a little part of that. So, as we're wrapping up, so the SI today has got some fundamental definitions. So the ground state of the height, well, the second is defined exactly. So this is again where we just chopped off and said we're done measuring it. The speed of light is also an exact measurement. And by the way, on that prior to 1983, they actually had a value for light down at three or four digits past the decimal point, but then they just made it 0. To your point, they just made those zeros to say we know that good enough. But we've got Planck, the elementary charge, Boltzmann, and the Avogadro. They have a number that's defined, but in parentheses relates to how the uncertainty there is in each of these measurements. So all of these values, these constants, have an uncertainty associated with them, and the luminous efficacy of monochromatic radiation, defining the candle, in lumen per watt, by the way, so I correct on that, the Candela actually goes back and talks about lumens there. And then, of course, the kilogram is still defined exactly as the mass of the artifact of the BIPM. Yes?
Why aren't they trying to measure pi?
Pi?
Why?
Well, pi is just an irrational number. You can compute it out to as many numbers, and that's the reality of it. So we do that out to, well, you just had 314. Did you celebrate Pi Day here?
Yeah.
Okay. So yeah, we do that a little bit of Fluke too. So, anyway, so that's the SI today. Well, we hope by May 20th of next year, this is what it should look like, and these are the numbers hot off the press for this. These are the proposed values. So right here, we kind of do, this is the unknown value. They want to make an exact definition. So this is the proposed value that it would be that the Planck's constant will be 6.626070015 times 10 to the 34 joules second, exactly, for that. And again, the elementary charge will have an exact definition. The Boltzmann will have an exact definition. The Avogadro will have an exact definition. And then, at that point, now the kilogram will be defined in terms of these natural physical constants. It will still be a meter. The SI will still be the second, the meter, and the kilogram. But it's just how they're defined is a little bit different. And that BIPM artifact will no longer be the definition. It will be a device that is measured and it assigned an uncertainty over time, so we can see its uncertainty change. Yes?
Right, so when you say they define exactly, so they say, okay, we have speed of light out a couple decimal places fast,
Yeah.
and we're going to truncate. Is there what is the deciding factor on where to truncate?
Honestly,
Is it arbitrary?
sometimes it's a little political, but it's also about measurement technologies and what's needed as well. So
Uncertainty.
yeah, it really does relate to the uncertainty that's required at that point. So the thought is that but at this point, back to we've set our measurement system. It's because our measurement system is a little bit arbitrary. Why would we say that the wave it's that many transitions and things like that? If they need any more accuracy, they can just add a zero now. 0.00 if we really wanted to say that. But to the point, that's, if you will, the king's foot.
But it's
now.
two needs, right? Because in the sense of the speed of light,
Yeah.
if we were in a situation where we're traveling speed of
Yeah.
light related distances, then we would probably need to.
That could be the case, or if we find out that Einstein was wrong in a general sense. Well, I mean, remember that Newton was right until Einstein looked at a bigger picture. Physics may give us more knowledge in the future. It could be that the speed of light is constant in a special case, as far as we know, and maybe there's a higher general form, but we don't know yet. I always leave myself open to that possibility. But the point is we'll fundamentally have kind of solved this and set these based on these natural physical constants. And I think so the last thing I'll just say is just acknowledgement to BIPM and Dr. Michael Stock, who loaned me the watt balance slides, and again to NIST for letting, and NRC for letting me take the pictures there for the watt balance and quantum Hall, or steal some of their pictures that they already had in there. And this is the symbol, the symbol of the new SI, with our fundamental constant, our SI base units, and then the fundamental underlying constants, Planck's, the speed of light, electron charge, etc. on that as well. So that is my presentation. So any other questions? Yes?
Does redefining the kilogram then, does that impact the Kelvin definition?
The Kelvin's going to be a little bit different itself on the Boltzmann constant more. So it's really going to be how much does the Boltzmann constant affect that triple point of water measurement. It's going to, and what it's probably going to be is they're going to be clever with a correlated quantity to be able to get to eliminate that variable to kind of keep the system intact the way it is right now. There's another scale called the International Temperature Scale of 1990, which is actually not the thermodynamic scale that we're really realizing on some of these points now. There's a slight difference at certain points, and that's where we kind of go down the rabbit hole in the politics of that, and how we realize and call temperature what it is today. So, yes?
Why is it that we can measure the frequency so much more accurately than everything else?
It's just the way we go about measuring it right now. For example, okay, even using that quantum Hall process, with electrical resistance, we can measure that out in parts in 10 to the 9, but it's just the experiments that we've done to measure measure laser wavelength gets us out into parts in 10 to the 18, so a billion times better than that. So